Let's move on to the next question. If A bar and B bar are 2 points, then R bar equal to 1 minus S into A bar plus SB bar represents a straight line. Second statement, if A bar, B bar, C bar are 3 non-collinear points, then R bar equals to 1 minus S minus T into A bar plus SB bar plus TC bar represents a plane. The options are, first option only 1 is true, second option only 2 is true, third option 1 and 2 are both true, fourth option neither 1 nor 2 are true. Now, if A bar and B bar are 2 points on a line, position vectors of 2 points on a line, and R bar is a position vector of any point on the line, what is it you can say? R bar minus A bar is a vector collinear with B bar minus A bar, AB vector. So how do we write two collinear vectors? One should be the scalar multiple of the other. So we can write R bar minus A bar to be S into B bar minus A bar. In other words, we can transpose this A bar the other side and get it in this form, 1 minus S into A bar plus S into B bar. Okay, that is what, where S is any scalar, S is a real number. For different values of S, we will get different positions of the point on the line. So R bar is a position vector of a general point on the line, then R bar minus A bar has to be parallel to B bar minus A bar or collinear with the B bar minus A bar. So which means that it can be expressed like this, which means that R bar can be written this way. So the first statement is true, no doubt about it. Coming to the second one, suppose you have 3 points, non-collinear points, whose position vectors are A bar, B bar, C bar. There will be a unique plane passing through them, because we can have construct a triangle out of them. A triangle is a planar figure, you can fit a plane through them. Now suppose R bar is any point on the plane generated by these 3 points. What is it you can say? R bar minus A bar, B bar minus A bar vector, this vector AB vector, C bar minus A bar vector, that is AC vector. These 3 vectors are coplanar vectors. So which means that we can write R bar minus A bar from here, that as lambda times some B bar minus A bar plus some mu times C bar minus A bar, which means you can write it in the form of R bar equals to, we can club the A terms, and then we have 1 minus lambda minus mu into A bar plus lambda into B bar plus mu into C bar. So we can write it in the form 1 minus lambda minus mu into A bar plus lambda B bar plus mu C bar, which means that here we have lambda, instead of lambda and mu, in the options we are given S and T. So we can even replace our lambda mu with S and T. So S and T being scalars, we can write 1 minus S minus T times of A bar plus S times B bar plus T times of C bar. Okay, so we have here, this is also another representation of the, where S and T of the plane, S and T are any real numbers or parameters of that. So the option 3 is right. Both 1 and 2 statements are correct. 1 and 2 statements, this is the statement 2 that we have. So both 1 and 2 statements are correct, and therefore option 3 is right. Answer is 3. The direction cosines of two lines are L1 M1 N1 and L2 M2 N2. then the value of L1 L2 plus M1 M2 plus N1 N2 whole square plus sigma M1 N2 minus M2 N1 whole square is equal to first option 1, second option 0, third option 4, fourth option 2. Let's have a look at this. Now we have two lines whose direction cosines are given by L1 M1 N1, L2 M2 N2. Now the sigma L1 L2 M1 M2, this summation L1 L2 plus M1 N2 plus N1 N2 is nothing but cos of the angle between them is equal to cos theta. So if you take the vectors, unit vectors along them, along the lines is L1I plus M1J plus N1K is a unit vector along it, and L2I plus M2J plus N2K is a unit vector along this line. Unit vector along the second line. So cos theta is the angle between them, clearly. That is, cos theta, if theta is the angle between them, cos theta is given by the dot product divided by the magnitudes. Since these are unit vectors, we can say it is sigma L1 L2 plus M1 M2 plus N1 N2. And now what about sin theta? Sin theta is given by the cross product of them, L1I plus M1J plus N1K, cross product with L2I plus M2J plus N2K, divided by the magnitudes. So what is the magnitude of this? That's only 1 here and 1 here. So sin theta is given by this, and that we can see easily that it's given by M1 N2 minus M2 N1 times I plus N1 L2 minus N2 L1 times J plus L1 M2 minus L2 M1 times K. That's what is sin theta given by. So now when you go for sigma M1 N2 minus M2 N1 the whole square, it's as good as taking the magnitude of this. It's nothing but sin square theta. Okay, sin theta is given by, in fact, the modulus of it, and that is the modulus of it. So modulus of this is given by M1 N2 minus M2 N1 the whole square, summation of that. So sin theta, square of that, under root of it will give me sin theta. So sin square theta will be sigma of M1 N2 minus M2 N1 the whole square is equal to your sin square theta. And we know that cos square theta plus sin square theta has to be 1, as we have this. So sigma L1 L2 whole square plus sigma M1 N2 minus M2 N1, M1 N2 minus M2 N1 the whole square is also equal to 1. So option 1 is correct. Option 1 is correct. Okay, let's move on to the next question. If alpha, beta, gamma are the angles made by a vector with the coordinate axis in the positive direction, then the range of sin alpha, sin beta plus sin beta, sin gamma plus sin gamma, sin alpha is the first option closed interval minus 1 comma 1, second option minus half comma 1, third option minus 1 comma 2 closed interval, and fourth option is closed interval 0 comma 1. Let's have a look at this. We have a line which is making angles alpha, beta, gamma with a positive x-axis, y-axis and z-axis. This is beta and this is gamma. we are asked to find out the range for sigma sin alpha sin beta. So let's have a look at this. First of all, if alpha, beta, gamma are the angles made by a line with the coordinate axis, then cos alpha, cos beta, cos gamma are the direction cosines, and cos square alpha plus cos square beta plus cos square gamma is equal to 1. We know this. Sum of the squares of the direction cosines is equal to 1, because if this cos alpha is L, cos beta is M, that's a standard notation, and cos gamma is equal to N. We know that L square plus M square plus N square is equal to 1 here. So here, from here, this I can write as 1 minus sin square alpha plus 1 minus cos square sin square beta plus 1 minus sin square gamma is equal to 1. This in turn implies that sigma of sin square alpha is equal to 2, because you have 3 minus sigma sin square alpha is equal to 1, which means that sigma sin square alpha is equal to 2. Let's keep this aside. This is a result here. Now one more thing here, sin alpha plus sin beta plus sin gamma, these three being real numbers, the square of them, sum of them and the square will have to be non-negative. Square of a real number has to be non-negative. What is this going to be? Sigma sin square alpha plus 2 times of the mixed sum, mixed products, sigma sin alpha sin beta. That's greater than or equal to 0. But just now we have seen that this is equal to 2. So therefore, sigma sin alpha sin beta will have to be greater than or equal to, let's transpose this to the other side, minus 2 by 2, and that makes it minus 1. So sigma sin alpha sin beta is greater than or equal to minus 1. Okay, so now so we got a lower bound for this sigma sin alpha sin beta. Now let's also get a upper bound for it. What's the upper bound for it? Here I know that sin square alpha plus sin square beta plus sin square gamma minus sigma sin alpha sin beta sigma sin alpha sin beta is always greater than or equal to 0. You know this result, a square plus b square plus c square minus ab minus bc minus ca is always greater than or equal to 0. This is an important result. This is simply half of sigma of a minus b the whole square, which is definitely non-negative. So using this now, this is 2, sigma sin square alpha is 2. So 2 minus sigma sin alpha sin beta is greater than or equal to 0, which in turn implies that sigma sin alpha sin beta will have to be less than or equal to 2. So now combining these two observations, what is it? Therefore, what is it I can write? Sigma sin alpha sin beta will have to belong to the interval close to interval minus 1 comma 2. So this is what we observe, and clearly option 3 is the right answer. Option 3 is the right answer. Let's move on to the next question. If ai bar plus j cap plus k cap, comma, I cap plus bj cap plus k cap, comma, I cap plus j cap plus ck cap are coplanar vectors, then 1 by 1 minus a plus 1 by 1 minus b plus 1 by 1 minus c is equal to, first option 2, second option 1, third option minus 1, and fourth option is 3. Okay, when are these 3 vectors coplanar? That means one vector can be expressed as a linear combination of other 2 vectors. They become linearly dependent also. 3 vectors being coplanar and linear dependency is one and the same. Here, so one vector, let's say the first vector ai plus j plus k, we can express it in the form of linear combination of other 2 vectors, that is I plus bj plus ck. That's the first vector. and plus mu times the second vector, where lambda and mu are two real numbers, I plus j plus ck. Now we can actually equate the like coefficients here. So what do we get now? A is equal to lambda plus mu, because I component can be equated to other I component there, lambda plus mu. So which in turn implies that 1 minus A will be equal to 1 minus lambda minus mu. What you wanted was 1 by 1 minus A. So 1 by 1 minus A will be 1 by minus 1 minus lambda minus mu. Similarly, let's equate the j component. Okay, so what do we have here? 1 is equal to b lambda, b into lambda plus mu. So from here, now can I write the value of b from here? What is the value of b? B will be equal to 1 minus mu by lambda. B is equal to 1 minus mu by lambda. So which gives me 1 minus b to be equal to 1 minus of 1 minus mu by lambda. So that gives me lambda minus 1 minus mu by lambda. So 1 by 1 minus b will be lambda by lambda minus 1 minus mu. Okay, plus mu, lambda plus mu, it will be lambda plus mu minus 1, because there is a bracket here. So lambda minus of 1 minus mu, so that makes it lambda plus mu minus 1 there, right. So 1 by 1 minus b will be this. Similarly, let's equate the k component. What do we get when we equate the k component? We get 1 to be equal to lambda c lambda plus, it is I plus bj plus k and I plus g plus ck. So when you equate it, so what we get is lambda plus mu c. Therefore this implies 1 minus lambda by mu is equal to 1 minus lambda by mu is equal to c. But what we wanted is 1 minus c. So 1 minus c, that makes it 1 minus lambda by mu. That makes it mu plus lambda minus 1 by mu. 1 by 1 minus c will therefore be mu by mu plus lambda plus mu minus 1. Here clearly now this 1 by 1 minus b we can write it in the form of minus lambda by 1 minus lambda minus mu, and this we can write in the form of minus mu by 1 minus lambda minus mu. Observe that this 1 by 1 minus a and this 1 by 1 minus b and 1 by 1 minus c, all of them have the same denominator, and if you add up all of them, 1 by 1 minus a plus 1 by 1 minus b plus 1 by 1 minus c is clearly 1 minus lambda minus mu divided by again 1 minus lambda minus mu, which is nothing but 1. So we have done. Option 2 is the right answer. Option 2 is the right answer. Let's move on to the next question, question number 5. If A with the position vector 2i minus j minus 3k, comma, B with the position vector 4i plus j minus k, comma, C with the position vector I minus 3j plus 2k, and D with the position vector I minus j minus 2k are given, then the vector equation of the plane parallel to ABC and passing through the centroid of the tetrahedron ABCD is, first option, r bar is equal to 2i minus j minus k plus s times 2i plus 2j plus 2k plus t times I minus k. Second option, r bar is equal to 2i cap minus j cap minus 3k cap plus s times I plus j plus k plus t into I minus k. Third option, r bar is equal to 2i minus j minus k plus s times I plus j plus k plus t into I plus 2j minus 5k. And fourth option, r bar is equal to 2i minus j minus k plus s into I plus j minus k plus t into I plus 2j plus 5k. So let's have a Look at the figure here. Tetrahedron. This is the plane ABC, let us say. The bottom one is the plane ABC. D is this point. Now we are interested in, let us say G is the centroid of the tetrahedron. That will be given by, if A bar, B bar, C bar, D bar are the position vectors of the 4 vertices of the tetrahedron, the centroid is given by, centroid is given by the average of all of them, A bar, B bar plus C bar plus D bar by 4. Moreover, the centroid divides the line joining the vertex and the centroid of the opposite face in the ratio 3:1. So if you take the centroid of the ABC face and join it with D, the centroid of the tetrahedron will divide it in the ratio 3:1. Okay, right. So using that fact and the position vector of centroid of a triangle is A bar plus B bar plus C bar by 3. Using that, we can get the position vector of the centroid of the tetrahedron to be A bar plus B bar plus C bar plus D bar by 4. Now what is our A bar here? A bar is the position vector of A, that is 2i minus j minus 3k, and B bar position vector of B, that is given by 4i plus j minus k, and C bar, the position vector of C, is given by I minus 3j plus 2k. D, the position vector of D bar, position vector of D bar is given by I minus j minus 2k. Now we are interested in the plane. To write the equation of the plane, we are interested to write the equation of a plane which is passing through the centroid of this tetrahedron and also parallel to our plane B bar ABC, plane formed by this ABC. Okay, so it should have been something like this. Now how do I write the equation of any plane? If you know one point on the plane, suppose we know one point on the plane as some G bar, and we know two vectors parallel to them, parallel to the plane, which are non-collinear, say some U bar and V bar are two vectors parallel to the plane, and G bar is a position vector of one point on the plane. Then this, with the help of this, we can write the equation of the plane like this. R bar is the position vector of any point on the plane. R bar minus G bar can be written as lambda times U bar plus mu times of V bar, because R bar minus G bar is going to be a vector in the plane. U bar, V bar are two non-collinear vectors in the plane. Two non-collinear vectors of a plane which lie in a plane can generate the plane. That means we can write any vector in that plane as a linear combination of those two non-collinear vectors. So we can write like this. Now here, instead of G bar, we have A bar plus B bar plus C bar plus D bar by 4, and instead of U bar and V bar, we can take AB vector. This AB vector is parallel to this plane, so you can take a copy of AB onto the plane. So we can take a copy of AB onto the plane like this. This is AB vector. Similarly, we can take a copy of AC vector also onto the plane. Right? And then we can write like this. So this is like our U bar and this is like our V bar. So using this, actually we will get R bar. What is A bar plus B bar plus C bar plus D bar by 4? So G bar will be given by clearly 2 plus 4 plus 2. So okay, that is clearly A bar plus B bar plus C bar plus D bar by 4. that comes out to be 2i minus j minus k. So now the equation of the plane can be therefore written as r bar minus 2i minus j minus k is equal to lambda times, shall we say, b bar minus a bar plus some mu times c bar minus a bar. That is b bar minus a bar and mu times c bar minus a bar, and that is clearly seen in the option 3. Also option 3, by verification you can see that option 3 matches with this. So that's how it is. That is, the key thing that we need to know is that when one point is given on the plane and two vectors, two non-collinear vectors are given on parallel to the plane, we can write the position, we can write the equation of the plane, vector equation of the plane this way. So let's say r bar is the position vector of a general point on the plane. R bar minus g bar can be generated with the help of this u bar and v bar. So what is u bar in place? U bar is our AB vector and v bar AC vector. So we can write like that. If a bar, b bar, c bar are three non-coplanar vectors and lambda is any real number, then the vectors a bar plus 2b bar plus 3c bar, comma, lambda b bar plus 4c bar and 2 lambda minus 1 into c bar are non-coplanar for all except two values of lambda, 2 all except one value of lambda, third option for all values of lambda, and fourth option no value of lambda. Now three vectors a bar, b bar, c bar are coplanar if and only if the box product is 0. Here, now we are given the vectors. Let us treat this a bar, b bar, c bar are non-collinear, non-coplanar. So a bar, b bar, c bar are non-coplanar. Okay, so therefore this implies this is given. This is a result that I have stated here. So since a bar, b bar, c bar are non-coplanar, we can say that a box product of a bar, b bar, c bar will be equal to, will be non-zero. Now we are interested in the box product of a bar plus 2b bar plus 3c bar and lambda b bar plus 4c bar. Also the third vector is 2 lambda minus 1 into c bar. Now this we can write in the form of, you complete this as each vector, let's write it as linear combination of a bar, b bar, c bar. So 0 into a bar plus lambda into b bar plus 4 into c bar. The third vector we can write it in the form of 0 a bar plus 0 b bar plus 2 lambda minus 1 into c bar. So this vector with respect to these three non-coplanar vectors has the components 1, 2, 3. So that will be written here 1, 2, 3. And then the components of this 0, lambda, 4. The components of the third vector 0, 0, 2 lambda minus 1, determinant formed by this, into box of ABC. So the box product of three vectors that are generated with the help of three non-coplanar vectors, we can write like this. This is a result. Now that is 1 into a bar plus 2 into b bar. So 1, 2, 3, the components of this a bar, b bar, c bar are written in the first row. The components of the second vector also is written as a linear combination of a bar, b bar, c bar, although it was given to be as a linear combination of b bar and c bar. I have introduced the scale, I have introduced the vector a bar with the scalar as 0. So 0 into a bar. So we write that 0 here, lambda 4, and then next we had only 2 lambda minus 1 into c bar. So which I am going to write as 0 into a bar plus 0 into b bar plus 2 lambda minus 1 into c bar. Now this, let's look at the box product. When is this box product? of these three vectors. Let's call this as v1, v2, v3. This vector v3. Box product of v1, v2, v3 is 0 if and only if the vectors are coplanar. But this is known to be non-zero. Therefore, when can this determinant be 0? When can this box product be 0? Only when the determinant is 0. And clearly the determinant, this v1, v2 is v3 box product is 0 if and only if the determinant, this determinant we have here is 0, because the later part is non-zero. Okay, so but when, for how many values of lambda can this be 0? What is the determinant? This is clearly in the upper triangular form. So upper triangular form determinant will be just the product of the principal diagonal entries. So what we get is 1 into lambda into 2 lambda minus 1 to be equal to 0. So that means that lambda is 0 or half. So for two values of lambda, only these three vectors can be coplanar. So for all but two values of lambda, these three vectors v1, v2, v3 will have the box product to be non-zero. The box product can be 0 only for lambda equal to 0 or half, that is only two values. So rest of the values of lambda, the box product will be non-zero, which means that for all except two values of lambda, these three vectors have to be non-coplanar. So the option 1 is right. Option 1 is right. Let's move on to the next question. The vector a bar is equal to alpha I plus 2j plus beta k lies in the plane of the vectors b bar equal to I cap plus j cap and c bar is equal to j cap plus k cap and bisects the angle between b bar and c bar. Then which of the following gives the possible values of alpha and beta? So we are given that the vector a bar lies in the plane of b bar and c bar and bisects the angle between them. Let us say b bar is this vector, c bar is another vector. Let us make them co-initial. B bar, what is b bar given by? I plus j, and c bar is given by j plus k. Now a vector, this vector a bar is known to bisect this angle between them. This is some theta and this is also theta. So then this vector would have been either in the form of, the a bar could have been in the form of lambda times b cap, that is b cap is the unit vector along b, plus or minus c cap, where again c cap is the unit vector along c bar. So let us write it. What is that? The vector a bar, he says, is either, is bisecting the vectors b bar and c bar. So it could have been in the form of lambda times b cap plus c cap or b cap minus c cap. So what is b cap here? B cap is I plus j by root 2. What about c cap? J plus k plus by root 2. Now your a bar, what is a bar given to be? Alpha I plus 2j plus beta k. Okay, then what about lambda times b cap plus c cap? Lambda times b cap plus c cap would have been I plus 2j plus k by root 2, lambda times of that. What about b cap minus c cap? That would have been I minus k by root 2, lambda times of that, lambda times of b cap minus c cap. For no values of alpha and beta, a bar can be equal, for no value of alpha, beta and lambda, a bar can be equated to this, because this does not have the j component. So this is ruled out. Moreover, observe that if you equate the components of this lambda by root 2 as a scalar here, this into I plus j, 2j plus k has to be equated to this a bar. So now observe that we could lambda by root 2, lambda into root 2 must have been equal to 2. So this, take lambda to be root 2 and then alpha has to be 1, beta has to be also 1, comparing these two here. Taking lambda to be root 2, then we can equate them and we have lambda alpha to be 1 and beta also to be 1. So clearly the option 2 is the right answer. Option 2 is the right answer. So let's move on to the next question, question number 8. If a bar, b bar, c bar are vectors such that a bar plus b bar plus c bar is equal to null vector and magnitude of a is equal to 7, magnitude of b is equal to 5, magnitude of c is equal to 3, then angle between the vectors b bar and c bar is first option 60 degrees, second option 30 degrees, third option 45 degrees and fourth option 90 degrees. Now how do we find out the angle between two vectors? We need the dot product. And we are given the magnitudes of b and c. How can we involve the dot product? And how can we find out the dot product with the help of this? Let's see that. Let's consider b bar plus c bar, that's equal to minus a bar, because a bar plus b bar plus c bar is 0. Now b bar plus c bar the whole square will be equal to minus a bar the whole square, which is nothing but this left hand side is b bar plus c bar dot product with b bar plus c bar, and here we have magnitude of a square. What about the left hand side? B dot b will give me magnitude of b square, c dot c magnitude of c square. So magnitude of b square plus magnitude of c square plus 2 into b dot c, and that is equal to magnitude of a square. Now let's substitute the values here and get the value of b dot c. So what is that? From here, magnitude of b square is 25, magnitude of c square is 9 plus 2 into b dot c is equal to magnitude of a square is 49. So b dot c will be equal to 49 minus 34, that makes it 2 into b dot c is 49 minus 25 minus 9, so that makes it 49 minus 34, that makes it 15 there. So b dot c by magnitude of b dot c, magnitude of b into magnitude of c is the cos of the angle between the two vectors b bar and c bar. Suppose b bar and c bar are two vectors, the cosine of the angle between them is given by the dot product divided by the magnitudes. So we have b dot c to be 15 by 2, the whole thing divided by, what do we have here? 5 into 3. So that gives me 1 by 2. Therefore cos theta is 1 by 2. This implies theta to be 60. Theta is 60. Therefore the option 1 is the right answer. Option 1 is the right answer. Let's move on to the next question, question number 9. If magnitude of a bar is equal to 5, magnitude of b bar is equal to 4, magnitude of c bar is equal to 3, what will be the value of a dot b plus b dot c plus c dot a and modulus of it, given that a bar plus b bar plus c bar is a null vector? First option 25, second option 50, third option minus 25, fourth option minus 50. Now a bar plus b bar plus c bar is given to be null vector. So what is a bar plus b bar plus c bar the whole square? That also has to be the square of a vector is the dot product with itself. So that gives us a 0 scalar. But what is this? This is magnitude of A square plus magnitude of B square plus magnitude of C square plus 2 into A dot B plus B dot C plus C dot A equal to 0. What is magnitude of A square? That is 25. Magnitude of B square is 4 square, that is 16, plus 9 plus that is 50 plus 2 into sigma A dot B is 0. So clearly sigma of A dot B has to be minus 25. But we wanted modulus of sigma of A dot B. Therefore, it's going to be modulus of minus 25, which is nothing but 25. First option is the right answer. Let's move to the next question. Question number 10. If A bar is equal to 3i minus 5j and B bar is equal to 6i plus 3j are two vectors, and C bar is such that C bar is equal to A cross B, then the magnitude of A is to magnitude of B is to magnitude of C are, first option root 34 is to root 45 is to root 39, second option root 34 is to root 45 is to 39, and third option 34 is to 39 is to 45, fourth option 39 is to 35 is to 34. Here we are given A bar to be equal to 3i minus 5j and B bar is equal to 6i plus 3j. C bar is equal to A cross B. So let's find out C bar first. 3i minus 5j cross product with this, I cross I will be 0, I cross j is k, so we'll get 9k. J cross I is going to be minus k, so minus 30 into minus k, that makes it plus 30k. That is minus 5j into minus into 6i cap is going to be minus 30 into j cross I. What is j cross I? Minus k. So minus of minus, that will make it plus there. And then j cross j is anyway 0. So we get 39k. Clearly the magnitude of C is 39, with this being a unit vector. K cap is a unit vector. What about this? Magnitude of A bar is equal to 9 plus 25, that is root 34. Similarly, magnitude of B bar is equal to 36 plus 9 under root, that is root 45. So clearly the magnitude of A is to magnitude of B is to magnitude of C is root 34 is to root 45 is to 39. And clearly the option 2 is the right answer. Answer is 2, second option. Let's move on to the next question, question number 11. If A bar cross B bar is equal to B bar cross C bar and is also equal to C bar cross A bar, then A bar plus B bar plus C bar is equal to, first option ABC, second option minus 1, third option null vector, and fourth option 2. First of all, A plus B plus C has to be a vector. Right away from that we can see that options 1, 2 and 4 cannot be correct because they are all scalars. So it has to be option 3. But then let's prove it. A cross B is given to be B cross C, and that's also equal to C cross C. Equating these two, we have here A cross B minus of B cross C to be equal to 0, null vector. This A cross B plus this minus of B cross A, I can write it in the form of C cross B equal to null. So we can even write this, taking B bar common, we can write this as A bar plus C bar, cross product with B bar is null vector. When is the cross product of two vectors 0? That means the vectors have to be collinear. So one can be expressed as a scalar multiple of the other, a bar plus c bar. We can write it as some lambda times b bar for some lambda scalar. Similarly, we will pick up this. We will consider this equation. We will even write, we can write b bar cross c bar plus a bar cross c bar is 0. Again I reversed this. B bar cross c bar minus of c bar cross a bar is 0. The cross product we can reverse, when you reverse it order you get a minus sign. So that minus sign has been absorbed here, and now you find that c bar is post multiplying on both the vectors. So we can take out c bar common. So we have here b bar plus a bar, cross product with c bar is equal to null vector. Again b bar plus a bar and c bar have to be collinear vectors. Therefore this implies b bar plus a bar, we can write it as some mu times c bar for some mu. Now what you could do is 1 and 2 from the equations 1 and 2, subtract 1 from 2. 1 minus 2, go for 1 minus 2. Let's go for 1 minus 2. So what do we have here? C bar, we have here a bar plus c bar, and therefore we can write c bar minus b bar to be equal to lambda b bar minus mu c bar. Now b bar and c bar are given, I can assume that they are non-collinear vectors. So when you have two non-collinear vectors, okay, when you have two non-collinear vectors, what is it you can say? This part, when you equate two linear combinations, now looking at this, now this is a linear combination of b bar and c bar, this is also a linear combination of b bar and c bar. One b bar and c bar being non-collinear vectors, we can equate the like coefficients. So the coefficient of c bar is 1 minus mu here, so 1 minus mu has to be 1. This implies mu is equal to minus 1. Or similarly, lambda is also equal to minus 1, equating the coefficient of b bar. Now either you use the value of lambda or you use the value of mu and put them either in the equation 1 or in the equation 2. Now a bar plus c bar is equal to therefore minus 1 into b bar, because lambda we got it to be minus 1 here. So I put back this value here, and therefore what do we have? A bar plus c bar plus b bar is equal to null vector. That's what we wanted to show, and option 3 is clearly right. Option 3 is clearly right. Let's move on to the next question. Consider the points a, b, c, d with the position vectors 7i minus 4j plus 7k, comma, I minus 6j plus 10k, comma, minus I minus 3j plus 4k, and 5i minus j plus 5k respectively. Then a, b, c, d is first option a square, second option rhombus, third option rectangle, and fourth option none of these. Now let's have a look at these options here. Option 1 says a square, second option says rhombus, third option says rectangle. All these three are actually parallelograms. Now for 4 points to be forming a parallelogram, suppose you have a parallelogram, the position vectors of the parallelogram are a bar, b bar, c bar, d bar. So this will be, the parallelogram, the diagonals bisect each other. So this is necessary and sufficient. What is that? A bar plus c bar should be equal to b bar plus d bar. This is necessary and sufficiency condition for a quadrilateral to be forming a parallelogram. Parallelogram if and only if a bar plus c bar is equal to b bar plus d bar. That is, sum of the position vectors of the opposite vertices has to be equal. Those two sums have to be equal. So this is the necessary and sufficiency condition. Now we observe that a bar, what is a bar? 7i minus 4j plus 7k, and c bar is I minus 3j plus 4k. What is a bar plus c bar? Clearly 6i minus 7j plus 11k. What about b bar? B bar is I minus 6j plus 10k, and d bar is 5i minus j plus 5k. Observe that b bar plus d bar is 6i minus 7j plus 15k. They don't match. This a bar plus c bar, they don't match. So the necessary condition is not necessary condition for parallelogram itself is not going through. So if it cannot be a parallelogram, it can't be a square, it can't be a rhombus, it can't be a rectangle. Hence the option 4 is the right answer. So option 4 is the right answer.